Okay then, folks. Right, all after one last-minute laptop reboot, I think we're good to go. Also on a very narrow stage here as well, so if I suddenly disappear, you'll know what's happened, and hopefully we'll be able to edit that out of any kind of video. Anyway, hello, hi. My name is Matt. Today I'm going to talk about Kotlin. Thank you for coming. And I should point out right at the very start, I work at JetBrains, and Kotlin is from JetBrains, but I am not an expert in Kotlin. I'm an interested amateur. I've done a couple of things with it. I've shipped a couple of features in Rider with it, but I'm not an actual expert. This is going to be kind of like an introductory sort of overview, take a quick look at it and a bit of a tour of some of the syntax and some of the interesting features, but I am not necessarily an expert, so please bear that in mind. Right, so first of all, what is Kotlin? Has anyone heard of Kotlin? Awesome. Awesome. It's so it's a programming language. It's a statically typed programming language. It's something we started building for ourselves. So the project started in 2010, and it hit version 1 in 2016, so it took a little while. And we're now at version 1.2, which was released about 8 months ago. No, it's longer, however long November was. And we kind of built it for ourselves. There were a bunch of things we wanted to do. We were looking for a new programming language. We have a strong investment in Java and in the JVM world, and we wanted to use a new language which was a bit more modern, using some of the more interesting features that modern programming languages have these days, and which was moving on and all kinds of stuff. And we had a look around, and we didn't really find anything that matched all of our criteria, and so we ended up building our own, which is cool. Fine, that's what you do, isn't it? Write your own programming language. So what are the things that Kotlin provides? What does it do? Why do we want it and everything? There are a number of things that we wanted to get out of it. So one of which was to have nice, concise code. So if you have used Java, you might be familiar with some of the verbosity of Java. It can be quite verbose, and you have to write quite a lot of stuff. Wanted to cut away some of that and make it a bit more efficient and quick and more productive with less typing, basically. We also wanted it to be a strongly typed language. We wanted it to be type safe. We wanted to make use of some advances in that kind of area as well. So attack the nullability problem, for example. And of course, it had to be very highly interoperable with our existing Java code base. We weren't going to throw away so many years' worth of Java code and start again. We wanted something which will seamlessly work and which we can work and migrate components over time or create new stuff in a new language while still working with the existing language. And of course, we wanted it to be tool-friendly because, hi, we're JetBrains. We make tools. The other kind of things we wanted as well, we wanted something which was a bit more sort of pragmatic. We wanted to take advantage of some of the features that you see in functional programming languages. I wanted to sort of bring some of those things in, but we wanted to take like a pragmatic view of it as well and work with some object-oriented and have a sort of a good mix of the two kinds of things there. But also, why Kotlin for you lot? You know, why would you be interested in Kotlin? What is it in there for you? So there's the argument of learning a new programming language. Of course, it's always a good thing to sort of try something new and learn something different. But a good argument as well is the reach of Kotlin. So Kotlin started out as a JVM language. That was our primary target, but it was never the only target. We always wanted to do more with Kotlin. So it started out on the JVM, started out to sort of replace Java with our own language in our environment. But it sort of quickly got picked up by the Android community, and it's got very popular there. And in fact, Google have taken it on as a first-class language in Android. And it is fully supported, and there's documentation and samples and everything written in Kotlin. They are making some changes to APIs and things to make it easier to write more idiomatic Kotlin sort of stuff. And so that's really been a big boost in the popularity of Kotlin. You know, we sort of started it for ourselves, but it is really taken off externally as well. So we've got stats on the number of lines of code on GitHub, and that's just kind of skyrocketed, which is cool. But we have other targets as well. So not just the JVM or running in Android or anything, but we can also run Kotlin in JavaScript. So we can compile your Kotlin down to JavaScript. Obviously, this isn't going to compile all of your Java libraries. You have to target sort of JavaScript libraries. And so as part of that, we ship a whole load of definitions for for JavaScript libraries based on the TypeScript definitions in definitely typed. And so you can now run Kotlin code on as JavaScript, and it can run wherever you can run JavaScript. So in the browser, in Node, and so on. And finally, and that's sort of production ready. That's shipping. You can go off and use that and build JavaScript type stuff, which is cool. We are working on another element of this. I don't know why I'm saying we. I'm not part of the team. So there is still work going on Kotlin native. So Kotlin is now targeting native code as well. And so this is using LLVM to compile down to native code, and it can run on Mac, Linux, Windows, iOS as well, so you can run it on your iPhones and iPads, and Android as native code. So this will then allow you to build, to have common code and share code between different platforms, and ship and have sort of your common code. The other targets we've got there as well are some of the IoT boards, so you can do some Internet of Things type programming with Kotlin, and also WebAssembly, which is going to be very interesting. Part of the work that's going on with that right now is a multi-platform story. So it's about building projects which can target multiple platforms at once, so you can have some common code, and your common code can then forward declare what it needs to be implemented in the platform-specific parts of the project, and then you can have the platform-specific parts which implement those. And this is the part of the project that we're working on most at the moment. So the technology is still there, it's working. We've shipped a couple of mobile apps which have been written in Kotlin, and they've been sharing code between the Android and the iPhone side of things. And it's all looking good. So that's some reasons for why you might want to have a look at it. So let's get on. Here's the agenda. This is what we're going to look at. There's a lot. Just kidding. That's a lot of things. This is not going to be an exhaustive look at things. We're going to have a look at a few things, walk around some of the syntax, some of the cool things, some of the interesting things that I like and that I want to point out to. But there is a lot more to Kotlin than what I'm going to show you today. But we'll dive in with an example, and you might notice that this is Java. So there's a lot of code here. It's really quite verbose, as we say. It looks like it's doing a lot of things, but it's not really doing very much at all. We've got some data coming in the constructor. We've got a couple of getters and setters for this data, and then a few utility methods there for sort of defining equality and toString and so on. That's the equivalent Kotlin. So it's perhaps a little unfair, but this is good. We really do take the conciseness to a limit. You're not going to see this level of reduction in code across the board. But there's a lot kind of going on in this one line of code. It's a useful thing to show and to talk about. And so there's quite a few things here. This is a class definition, and when compiled, you'll end up with the same code as you did with the Java. That was there. So some things to talk about with this is the use of modifiers. We use modifiers quite a lot in Kotlin. It sort of reduces the keyword count, as it were. But you can apply modifiers to various things like classes and functions, and it changes the way these things behave. So the data modifier here defines this as a data class, and when the compiler sees that, it will generate the extra functions that we saw in the Java example. So this one will tell the compiler to generate the clone method and the comparison method equality to treat it like a value class. The next thing of interest is the primary constructor. This is the way of getting data into your class, and why, if you've got a class declaration, why add an extra couple of braces, an extra couple of lines just to define a constructor, when we can do it all here as part of the actual declaration itself. And as part of that, we actually get to declare variables as well. So the parameters that get passed into the constructor, if they've got the val or var keyword, means that we will declare the compiler will generate these as properties. So it'll generate getters and setters here. By default, it's public. You can add the private keyword as well, so you can create private properties off the back of it. But these will create public properties. And the different keywords do different things as well. So val will create us an immutable public property. So the compiler will only generate a getter for this. And the var keywords will give us mutable public properties. So we'll get getters and setters. OK, so we've got our class declaration. How do we create a new instance of this? And the really interesting thing here is that there's no new keyword. We don't call new, we just call the constructor. So the constructor is just another function. And you call that as a function, and it returns you back an instance of the class. And this is really cool now because then you can pass around constructors as functions and do interesting things with that. Other thing to point out here is the type inferencing. So we're assigning that to a value type customer, and the compiler is doing type inferencing there. So does everyone have a C# background, by the way? Or most of you? OK, so I'm kind of going to assume a bit of C# knowledge then. So it's like the var keyword. It's statically typed. The compiler knows what's going on here. It's assigned it knows the value at compile time. It doesn't change. There's no dynamics going on. It's just type inferencing and shorthand for typing. We can specify the type if we want, but it's just redundant in this case. So the val keyword we've got here is for a read-only value. It doesn't change. It's just read-only. You can also use the var keyword then as a mutable variable. And this bit of code here as well is a screenshot from the IDE, and it just kind of shows you things like parameter hints. So again, putting in the tooling into this behind this, into the language, when you're passing literal values around, like a literal integer or a string literal, it's sometimes hard to know what those parameters should be. So the IDE can show you parameter hints there. Nice little touch there. All right, a slightly more interesting but also contrived example. It can show you a few more things going on. There's another class declaration going on here. Some of the Java heritage does show through. We've got packages at the top. We're declaring a package, and we've got import statements. This isn't Java. This just looks like Java. It's effectively declaring a namespace, and so it's and then bringing code in from other namespaces. So this is showing some Java interop going on here. We're pulling in the Java random class, and import statements pull in a class at a time. You can use the Java-like wildcard star to bring in a whole namespace, a whole package. But it's just bringing namespace code in to allow you to use it. So we can declare a class. And that class then has some properties which we declare as part of the primary constructor, just as we've seen with the data class. But this one's got some more things going on inside it. It's got a function inside it, which is just returning, it's just printing something out and not doing anything much. But we're declaring a couple more properties in there as well. So we've got an area property and an isSquare property. The isSquare property is a computed property, and so it's got an explicit getter. There's no setters there at all, but it's just doing a getter, and it's just doing a calculation returning Boolean. The area property is slightly more interesting because it's delegating. So this is it's a lazy property. It doesn't need to be lazy to calculate area. It's not that difficult, but this is lazy, and it'll only get called the first time you access that property, and it will work there. And this introduces a feature of Kotlin's called delegation, which we can do a whole bunch of different things with. So we can have things like observable. We can delegate a property to make it observable, and we can also create custom delegate types as well. So we can do some fun things there. The other thing we can show in this little snippet really is the create random rectangle function, which is a top-level function. It's a package-level function. We don't have to declare functions inside a class. It can just be top-level. And that's, again, creating instances of classes without the new keyword, and that's pretty much that. So does that all kind of make sense as it looks like? Awesome. So we'll pick up a couple of other interesting points about Kotlin as we look at a few things. One of the key things is that it's expressions everywhere. Everything has a value. So apart from sort of declarations, like value declarations, everything itself has a value. Everything has a type. And this includes control flow keywords. So if you're using the when keyword, which is like switch, it's for pattern matching. If is also an expression, try, and even throw are expressions. So Kotlin doesn't have a ternary operator, so the something colon something, something question mark something colon something. It doesn't have that. You just assign, you just use the return value, as it were, of an if expression. So if itself has a value. Throw is an interesting one. If throw has a value, but what is that value? Which means it's that sentence you've all been wanting to hear. Let's talk about the type system. So Kotlin has its own type system. Kotlin started life as its primary target was a JVM, but it has its own type system. It doesn't use Java's type system. And everything is an expression, so everything has a value. So there are some changes and some differences between Kotlin's type system and Java's type system, or any other target that it has. So one of the key things, because everything is an expression, means that there's no void keyword. There's no void type. Void isn't even a type. Void is a lack of types. So there's no void. If you need to have something which doesn't really return anything, you can use the unit type, like you can in F#, for example. And unit is a type and has a single value, and it's just something which is useful for when you're having things like generics. Void doesn't work with generics. You can't pass it around in there, whereas you can have unit as part of your generics. The root type is a type called any, and it's not Java's object. It's its own type, although when you're doing Java interop, they do map nicely together. And then finally, we get to the type which is all about throw, and that's the nothing type. Nothing is a little bit special. There are no instances of nothing. You can't have an instance of the nothing type. What nothing really says is that this is the end of execution. So if we have a function that returns nothing, or its return type is nothing, then that function will never end. It'll never finish. It'll usually throw or halt the program or something like that. So this can then be used by the type system to know that execution doesn't carry on through past this point. You can use that when you're doing type checks, for example, and you can know that there's a certain value here, or that the control flow of the program has finished at this point. If you are doing Java interop, the type system hides away the differences between Java's primitive and wrapper types, so you don't have to worry about int and integer. So you just use the Kotlin integer, and it will be fine, or be good. And then, of course, there are functional types and nullable types, which we'll look at in a minute. There's generics as well, and I'm going to get a bit hand-wavy here because there are generics, and that's all I'm really going to get into. There's a bit more stuff going on here with variants and type reification and all that kind of stuff, but let's just say there's generics. It's closer to Java's generics than it is to C#'s, but it's still its own kind of thing. Still on the type system, Kotlin has the idea of Smartcasts. So, for example, this little snippet here, we've got the parameter x, which is of any type, so we don't know what it is. It's the root, it's the equivalent of object, and we're doing some pattern matching to see what kind of type it is. And as soon as we said, well, you know, when it's a string, the compiler says, okay, it's a string. I'm going to treat it like a string. And so you don't have to cast, or you don't have to create a new variable of the string type. The compiler now just knows that it's a string, and you can use the properties and methods, and functions as normal. And the IDE will show you this as well. So it'll highlight the code and then give you the appropriate code completion too. All right, null safety. This is a bit more interesting. By default, so Kotlin has tackled the whole null safety issue by saying that types are non-nullable by default. So if you have a string type, it's going to have a value. You're not going to get a null value of string. And so you can quite happily call length on use the length property on a string, and you know it's going to be fine. It's going to compile, and it's going to be good. And you can't assign null to a non-nullable string. There's going to be a compile time error. The compiler will help you out here and will tell you that you can't do this. But of course, you can have nullable types as well. So we use the question mark syntax to declare a type of being as being nullable. So you can have string question mark, and so you've got a nullable type. This can have a value, or it can have null, and so you don't know what it is at the point you're using it. So you can assign null to it. You can assign an actual value to it, but you can't call just length. You can't call b.length. Because that could be null, and you could dereference that, and you could get an exception. So the compiler will tell you, no, you have to do some kind of null check first. And you can do an explicit null check, and you can compare against null and work with it from there. Or you can use the conditional access operator, the question mark dot, and this gives you, this says, if b has a value, return the length property. If not, return me null. That then means that the type of this expression that returns back is nullable int. So the null kind of propagates through, and so sooner or later you're still going to have to do null checks. You can also tell the compiler that you don't care. that this is definitely going to have a value, and you can use the not null assertion operator, the double exclamation mark, and this will sort of discard any kind of warnings and errors that the compiler would normally give you, and it will just go for it. You're going to get a runtime assert if you get it wrong. This is you basically telling the compiler that you're smarter than the compiler, so go and do it. You're probably not smarter than the compiler, so probably don't use this. Interop is an interesting question, because once you're in the Kotlin world and the Kotlin type system, then you kind of know what the nullability of everything is as it goes through, and the compiler will follow that through and trace it through and tell you. But when you are accessing third-party APIs, whether that's from the system, whether that's from another vendor or another open source project or whatever, then you're not necessarily going to know the null safety of those types. And so how do you deal with this? How does this work? So Kotlin has the idea of platform types, and this is the type then of the return value, for example, of an API, of an unknown API. It gets treated as a platform types, as a platform type, where the Kotlin and the compiler basically says, we don't know. We don't know whether it's null or not null, but what we will do is ignore it. You're on your own. You figure it out, effectively. You don't get any guarantees. You're not going to get any warnings. When you try and dereference it, it's up to you. So you now have potential runtime asserts. And so you have to sort of code with this and work with this and try and make it work. But on your side, there are a whole load of annotations which you can use. And the compiler ships with some annotations for various things. So in the JVM, we've got a whole load of annotations which will help you and give you that nullability information. If the compiler sees this information, it will treat them like Kotlin types, null or not null, and then you'll get the appropriate warnings. But other than that, you have to kind of work with it yourself. All right. Let's move on to functions. There's a whole load of stuff on functions. They're a lot of fun. I'm sorry. Functions, you define them with the fun keyword, and you can define them kind of anyway. You can define them inside a class. You can have member functions, and again, you get to see some more modifiers here. Classes and functions are sealed by default. They're final by default. You cannot derive from things. You have to design for inheritance. And so you have to sort of choose to inherit with that, and use the open keyword then to sort of the open modifier to say that something can be inherited from. Functions can have default values, very much like in C#. You can have named parameters as well when you're calling things. You can use the override modifier to override things. You can have top-level functions, and you can declare everything there. You can see the function signature we've got here. We get to specify the type of the parameter. We also get to specify the return type. But then we can start to be a little more terse. So if the function itself is just an expression, then you can write it as an expression. You can say the function method equals x times 2, for example. And if the compiler can do type inference on this, you can then ignore the return type as well. So you can sort of reduce the amount of typing that you have to do to declare your functions. And functions can be everywhere. So they can be inside a class, they can be top-level functions, and they can also be inside functions as well. So you can have local functions. And these will only live in the scope of this particular function where it's declared, and it can share then sort of information like closures and access the variables and properties that are available to it there. A couple more modifiers, which are really useful. We've got the tail rec modifier for tail recursive functions. So a tail recursive function is a recursive function where the very last thing it does is call itself. And this can be optimized away because we don't need to keep the call stack here. We can then sort of optimize this, and the compiler will take this code and rewrite it into an iterative loop. So we don't have to kind of push things down and have a big stack with the chances of potential stack overflow exceptions. We can sort of rewrite it as an iterative thing. Does that make sense? Yep, good. Another useful modifier is the infix modifier, so you can then change how a method is called. If you've got a function with 2 parameters, you can call it as an infix parameter. So you can have, instead of saying, for example, a.2 brackets 1, you can do something like b2 2. And this particular example now is going to create a new instance of the pair class with those 2 parameters. The syntax here is a bit interesting. First of all, we've got a generic function, and so we're not declaring what the types are up front because all we really care about is stuffing them into a pair class. And the other thing is we've got this a.to syntax, and that's for extension functions. So we can have extension functions and create extra functions which look like instance functions on existing things. So in the same way that C# has extension methods, Kotlin then has extension functions. It works in pretty much the same sort of way. It's compiler magic, compiler rewriting. It looks like instance methods, but actually they are just standard functions and static methods and called like that. The way it's declared, the way it's declared is very different. So instead of having a parameter which you pass in as the first parameter and an extension method in C#, we declare the type that this applies to as part of the method name. So we've got mutable list of t.swap as part of the name, and then that particular value is available as the this keyword inside the function. So if we now kind of look back at our infix method, this makes more sense. We've got a.to. We're saying this is an extension method on the generic type a, so it pretty much applies to anything. And then the this keyword is now being used as part of the creation of the pair. And because of the syntax declaration we have whereby the type we are extending is part of the method name rather than a parameter, we can actually use this for extension properties as well. So we're not limited to just extension methods, but we can have extension properties too. But an extension property can't declare any data, it can't hold its own data, it can only work with existing data. So here it's accessing the size property on the list of t via the this parameter, which we don't have to specify. But one of the things which is interesting here is that I've been showing you just function declarations and property declarations. There's no classes in there at all. We can have top-level functions and properties, or rather package-level functions and properties. So this kind of removes the biggest need for utility classes. So we don't need to have to define our utility classes, which are usually just a static class with static methods and static properties to do helper stuff. Instead, we can put they're just kind of containers, they're namespacing. We've already got namespacing, it's packages. And so we can just put everything at the top level and access it there. And so we don't really need these utility classes, which is a very nice feature. And we kind of actually, Kotlin takes it even further than that, and it gets rid of the static keyword completely. So you don't have static. And this is a little weird, and you don't, it does take a little while to get your head around, but on the whole, you don't tend to need it because you just put everything as a top-level function or a property. And also top level, you can have fields as well, so you can put data in at the namespace package level as well. But there are times when you do want to have the equivalent of a static function, and Kotlin has something here as well. And this is also a little bit weird. It works a little bit differently. Kotlin has the idea of a companion object. And this is actually an instance of an object. Rather than static properties and things, you get a companion object which is created alongside it. There's one instance per class, and it's an actual object. It's created. But you access it like a standard static method. So here we've got a companion object with a create function, which is just calling the constructor to return back. It could be doing a much more interesting sort of factory class kind of thing. But this is just creating a new instance. And you just call it like myClass.create. But because it's an object, you can do more interesting things with it. You can have an object which has got inheritance. It can implement interfaces. You can even create things like extension functions for companion objects. I'm not entirely sure why you'd want to do that, but you can. It's an interesting thing. It's something I'm not entirely sure I would use very much of, but it's available and it's there to you, and it's fun. It's interesting. All right, everybody with me so far? Everything okay? Good stuff. FirstClass functions. So we've done a lot of things with functions, for declaring them and everything. But we also get to use them as first-class objects as well. So we get to pass them around, we can return them, and we can work with them as such. The type signature for that is very similar to it is very similar to normal type signatures with brackets to denote the parameters that you're using, and then a return types there. So here we're passing in a parameter p, which is going to accept, is going to be a function which accepts one parameter of type t and returns back a Boolean. And here we can just loop over a list, call the method, call the function, and we're good. We can pass named functions there. We use the colon operator to pass in a named function. We can do like a named function from the current class is odd. We could do string.toInt to pass through, or we can even pass through something which is bound to a particular instance. So we can say pass in is odd, but only the one for foo. So it's already got an implicit context there. And you can also pass in constructors as well. Because now we're treating constructors as just a normal function, you can pass that in to other methods. Or you can return those as well. So you could return a constructor as the return value of a different function. Or you can create your own. You can use the string, the function literal syntax with the braces. You declare your parameters inside that. You do the arrow, and then you're the body of the method itself. And that's one way of doing it. If the parameter, if the function is the last parameter in a function call, you can also take it outside of the parameter list. And so you can have the parameter list, close it, and then have the body of the function which you're passing through. And you can also shorten it down if your function only has one parameter. You don't have to declare it, and you can just use the keyword it. So you can actually sort of reduce things down very much and make your code even smaller. And in fact, if we rewrite this as an extension function, where the passed-in function is the only parameter, we don't have to use parentheses at all. So I can do items.any, no parentheses, and then the body of the function itself. And we can use this now to sort of build DSLs and build an interesting sort of domain-specific language and other useful stuff there, which we'll have a look at shortly. But one of the problems with first-class functions and passing them around and chaining things together is that they can be expensive. So you're paying for the cost of the closure to grab any variables that you've got, and then you've also got the actual cost of the function call itself as well. And so if you're doing this a lot, for example, in C#'s link, while it's very good and very expressive and very useful, it can be expensive in terms of allocations and in terms of overhead of calling functions. So Kotlin has a way to work with this as well, and it's another modifier, and it's the inline modifier. And this tells the compiler to inline the function body that you're just declaring into the caller. And so here we could do something like creating a lock function, or we could create something like C#'s using statement as an inline function. And what it'll do when the compiler sees that, it'll pull all of that code in. So we lose the overhead of the closures, we lose the overhead of the method call as well. But there's a bit of a gotcha here, and this is something which can be a little unintuitive until you realize what it's all about and what it's for. So what does this print? This bit of code here, we've got a for each extension method, which incidentally I'd hate to see in C# because we've got a nice keyword which already does this, and you've got the overhead of lambda captures, you've got the overhead of method calls for every item that you've got. But if for each is inlined, that all goes away, and so this is fine and nice and okay in Kotlin. But what does this print? When we hit the value 3 in our list, we've got a return statement. So does it print 1, 2, done, or does it print 1? Who says 1, 2, done? Yeah, you're all very smart. So if we have a quick look at it here, we can see it and we can run it, and it prints 1, 2, and then it comes out. This is because of what we call non-local returns. So a non-local return is this return statement here, which is not returning out of our lambda. So we've got a lambda here. It's not returning out of that. It returns out of the overall containing function. So it returns out of main itself. This kind of feels a little unintuitive to start with. But the idea is that by doing this, you can actually write code that, that looks like language features, effectively. So here we've got something with a for each statement, with a for each function. But now that looks more like a language feature with for each. If you wrote it as using the for each keyword, for example, in C#, that return would make sense, and you would expect it to return out of the containing function. We can also do non-local returns as well. We can actually, excuse me, we can add a label to it as well. So we could say, we can return back, but return to this point here. And so if I do sort of control-click there, it'll take me back to that particular scope. And if those are nested, you can give them labels, and you can return back to a particular point should you need to. But on the whole, you have this idea of non-local returns. So yes, it's all about allowing inline functions. And that's only the case for inline functions as well. It's not for all functions. But it allows you to behave like a language feature. Because if you, as I say, if you'd written that as a for each statement in C#, then that return would make sense. Yeah, we've already shown you that. Right, last thing to do with functions, and I think this one took me a long time to get my head around. It's a bit weird. It's called lambdas with receivers, which is just a fancy way of effectively saying local scope extension functions. So what we're doing here is we're creating a new lambda, but you can see that the syntax for declaring it is very much like the extension function syntax. We've got int dot. So we're saying this applies to int, the objects of type int. And then it'll take a float value, return an int, and we get to do something. And we've got a this keyword in here as well. And so basically we've created an extension function, but we've assigned it to a value. Rather than having to create it as a top-level actual thing, we've assigned it to a value, and we've got it there. And so we can call 42.sum and pass it around. This might be slightly more obvious if we write it as a function, as an anonymous function in the declaration instead. Because again, it looks like it's an extension function with the int dot syntax and the this statement. And again, this is also very useful for domain-specific languages and type-safe builders, which I can show you now. So we can build, we can use this to build sort of domain-specific languages. So you can have some code which looks like this with the HTML and the body. It's kind of nested. It's actually now looking more like data than it is code, but those are function calls. And those function calls then are type-safe, and they have scope, and they have the this statement at those points is a particular value. This might be easier to show in code. So let me get rid of that. So we have an example here which is doing the same sort of thing but more fleshed out. And you can see here we've got our HTML call here. That's actually a method call, a function call. If I navigate to it, we can see we've got a function call here. And the signature of this is accepting a lambda with receiver. And it's saying effectively a locally scoped extension method on the class HTML all capitals. And I can go to that HTML all capitals class, and that defines a couple of extra functions, head and body, which then take in, again, another lambda with receiver, another locally scoped extension function, but this one is scoped to object of type head or object of type body. If I just jump back to the HTML one, the contents of this function is we call new on our HTML class, and then we call our locally scoped extension function, our lambda with receiver. And we do it on that new instance of the class. So if we go back to what we have here, we can see again that the IDE is giving us some hints here, and it's saying this, the implicit this keyword is of type HTML. So down here, I could actually type this dot, and I'll get code completion of the current type. And so I can create body and head. I've already got head here. If I do this, the this now has changed, and it's of type head. And so I've got things I can do with the type of head. And we can use this then to sort of build an entire sort of domain-specific language to build a type-safe builder, because I can only do appropriate things in there. If I'm in H1, for example, let's just open that out. And if I do this here, then I couldn't put a title in there because there's no title method there. It's type-safe. So it's nice and useful. Does that make sense? Anybody got any questions about type-safe builders? Cool. OK. Kotlin also ships with a standard library. So it's not just about the language and the compiler. It's got a standard library. It's a fairly small standard library. It has a bunch of inline functions and a bunch of other things. And it is really there to sort of encourage idiomatic usage of Kotlin and to make it more Kotlin friendly to be able to do things. So it has a handful of things. It's got the core type definitions. So, for example, the any type that we're talking about, and the string and integer types, which hide the Java wrappers, for example. They're defined there. It also defines some collections and sequences. So because we target very different platforms, we also want to have some collections and sequences that you can use here. These are wrappers around the platform types, and they provide interfaces that represent mutable and immutable views on those wrapper types. So while we've got a mutable or immutable view of it, the underlying collections are not necessarily immutable, but we've kind of got that way of working with it. There's also methods for creating collections and for lists and sets and maps and all that kind of stuff, which is good. A whole bunch of higher order functions, so we can do our filter, map, reduce kind of method chaining, function chaining, and working with that. There's regular expressions in there as well, again for making it sort of idiomatic Kotlin for working with regular expressions. Bunch of stuff for interop, working with both the JVM or for JavaScript, and some type-safe builders. So, for example, the JavaScript version of the standard library includes definitions for working with the DOM. So you can then have like a type-safe builder for working with the DOM itself and working with the windows. And then there are also primitives for coroutines. And coroutines are a lot of fun, and we're going to have a look at those. So what is a coroutine? Coroutine, well, there's a nice big Wikipedia-style definition for that, but the key things there are non-preemptive multitasking and suspending and resuming execution. Basically, they are just sort of super lightweight, user-scheduled threads. They're not threads, not like operating system threads, but they are a thread of execution. So it's like tasks in C#, if you're familiar with that, but it works in a very different manner. Coroutines are all based on the idea of suspending functions. So it works slightly differently to how you'd be used to in C#. It's yet another modifier on a function declaration, and it's the suspend modifier. But it does a very sort of similar thing. When the compiler sees this, it will rewrite that function to be a state machine. And it'll create like a state per suspension point. So it'll do some work, allow you to then yield and go off and do something else. It'll have a callback, and it'll come back, and it'll run the next step, and it'll go off and do that. So if you're familiar with C#'s yield, return iterators, and also async await, it's a very similar sort of mechanical process of rewriting that code into a state machine. But the big difference is that all the behavior actually comes from library functions, not from the compiler. So when C# is working with yield return, it rewrites your code and does yield return. It doesn't allow you to do anything else. If you want to use async await, it's a different process to build a different state machine and excuse me, work with that, and it'll return back task of T or items that look like task of T. Whereas Kotlin will basically just do the mechanical state machine rewriting and then leave everything else up to library functions. So then you need to be able to launch a coroutine to start it off, to kick it off. And for that, we've got the idea of coroutine builders. So you have a method such as launch here, which is a normal function, but it takes in a lambda, which has got the suspend keyword. So it takes in a suspending function, and it will do something and kick it off and make it work. And these coroutine builders use the standard library primitives to start a coroutine, but they're just sort of just functions. So they can do a whole bunch of things. They can do lots of different things and kick them off in different ways. And you can also pass in different context to it. So, for example, launch here has got an override where you can pass in a UI context, which means that this will always switch back to the UI context before continuing with the coroutine. And there are other coroutine builders as well as part of the standard library. So launch is a sort of fire and forget, throw it on the thread pool, just go off and do it kind of thing. There are other ones such as async or run blocking, and they will do very different things. Another interesting thing with this is is another difference with C# in that await is just another function. So when you're working with async await in C#, await is a keyword. You have to await an asynchronous function before it can do anything. If you don't await it, you get back a task of T and you have to do stuff with the task. Kotlin has it with sort of the opposite way around, whereby you will always have a suspension point, and if you want to work with the equivalent of task of t, you have to do something else. So this is a very sort of explicit design choice by the Kotlin team as well. So they wanted it to be, they wanted coroutines to be sequential by default. So you didn't have to opt into this sequential behavior. It just is the normal sort of thing. So as you run down, you hit a suspension point, you go off and come back, and you keep on doing that. Whereas with C#, unless you use the await keyword, you'd run through everything and you'd have a bunch of tasks which you have to manually manage. So in C# world, you kind of opt into this sequential behavior, whereas in Kotlin, you instead opt into concurrent behavior. And that's what the await function gives you, is the way to opt into concurrent behavior, because await will then return you back information which you can then work with, and you can have the similar sort of thing of task of t. In Kotlin, it's called deferred, but you can do the similar sort of thing with that and combine those tasks and run those sort of concurrently. And because coroutines are just about rewriting everything into a state machine and then providing things by library functions, iterators can be built with coroutines as well. So it's not just about asynchronous behavior or about concurrent behavior, but it is things like iterators. It's all about things where you want to suspend execution. So this is the equivalent of C#'s yield return iterators. You have just a different coroutine builder, and then a function. Rather than having to add a keyword yield return, you just have a yield function, which is a suspending function, and that'll return back the value, and you can then sort of work with this in a sort of continuing manner. Does that make sense with coroutines? Anyone got any questions so far? Cool. All right, so to wrap up then, it's how do we get started? And the easiest thing to do is to go to trykotlin.org, which is a great site. It's an online site, obviously, unlike the offline websites. And it gives you like a whole set of items which you can run yourself, of test code. I know this is quite small, but let's zoom in a wee bit. There, it gives you sort of test code which you can run, and in the browser there you can just click run, and we'll get the output then showing down at the bottom there. And there's a whole load of samples which are available here, and it can show you a bunch of useful things. You can pass in parameters to the method, and you can run that, and it'll print the outputs down at the bottom. And then there are the cones as well, which allow you to then, it walks you through a whole load of tasks. And so you can have a test and a task, and it will then check to see whether you got it right, and it'll walk you through the language. So that's a great way of getting going. And there's, excuse me, like example code for the Kotlin in Action book, and a whole load of things which you can execute in the browser. Look at that. There's even a convert from Java button, which is nice. And of course, that's a useful way then for working with some code samples and examples in the browser, or for trying to just figure out a small thing. But if you want to actually write an app with this, some kind of application, then you want to use some appropriate tooling. Obviously, we can do it in IntelliJ IDEA or Android Studio, but we've also got plugins then for Eclipse as well. So you can use Eclipse to build Kotlin code, or you could go hardcore and use the command line compiler. But IDEs. So that's the KotlinLanguage.org. The other thing we've got, which is very useful, is the documentation. The documentation is very good. There's a lot of reference docs, and you can also run code directly from the reference docs as well, which is really cool. And then there are tutorials in there too. So it's not just the reference for those particular functions, but you've got the tutorials which will step you through things and work with things. So that brings me to the end of everything, really, and there are some links available here. So KotlinLang.org is where the reference site is, where the documentation of the tutorials are. Try.kotlinlang.org, not try.kotlin.org. Try.kotlinlang.org is where you can actually give it a go in the browser. Kotlin itself is open source. It's Apache 2 licensed, and so you can join in if you want to. You can download it, you can build it, you can raise issues, suggest features, and so on. JetBrains/Kotlin on GitHub. There is then, confusingly, the Kotlin organization on GitHub, and this has got things like the extensions to the standard library. So some of the coroutine information is there, some of the type-safe builders are there, and more interesting stuff going on in there. Kotlin native is being built under the JetBrains org as well, and so that's going to be the code for compiling down via LLVM to native code or WebAssembly or Internet of Things or whatever. And it's also where we're working on the multi-targeting, multi-platform project system. That's me. And then finally, the last link then is a very good presentation about coroutines. So if you want to find out a little bit more about coroutines, how they work, and some of the decisions behind it, that's a great presentation by one of the team who actually worked on the feature itself. And I think that's it, really. So unless there are any questions, I'd like to thank you very much, and thank you. So does anybody have any questions? Hello, yes, question. Are we ever going to target .NET? The short answer is probably not. I don't know. I still need to find out the full long answer. I believe it's to do with the type system, and in particular the generics and how generics work. Because the decision was made to follow the because we're running on the JVM, generics have to have type erasure, so we don't encode the generic type information as part of the compilation. The JVM doesn't see it; it throws it away. Whereas C# and CLR needs that information, and so we've kind of got a conflict there already. We probably could encode the type information as part of the Kotlin compilation and have that as some sort of metadata sidecar that got distributed with your package, but that would then be expensive to run on JVM, and that. And so far the answer is no. It's a bit too hard. Yes, we just need the demand. So if you all ask for it for .NET, then maybe. Yeah, yes. Tell Hadi. Hadi will definitely get it sorted. Yes.